Welcome to the Bedtime Scientist, to tonight's journey into one of the most profound mysteries that has captivated human minds for millennia. Whether you're a truck driver pulling through the late hours, someone winding down after a demanding day at the office, or simply curious about the cosmos from your cozy corner of the world, you've found the right place. Drop a comment below telling us what time it is, where you are, and which country you're watching from. I genuinely love seeing how this content travels across time zones, and if these explorations help you drift into peaceful rest, a like and subscribe really does help the channel grow. Tonight, we're diving deep into a question that has puzzled humanity for centuries and continues to shape our understanding of reality itself. Why does light have a speed limit? It's a deceptively simple question that opens doors to some of the most profound discoveries in physics. The speed of light isn't just another number scientists measured, it's the cosmic speed limit that governs everything from the tiniest particles to the largest structures in the universe. Picture this, you're standing on a perfectly still lake at dawn, and you toss a pebble into the water. Ripples spread outward in perfect circles, each wave moving at a specific speed through the water. Now imagine if those ripples had an absolute maximum speed they could never exceed, no matter how hard you threw the pebble or how many pebbles you threw. That's essentially what we're dealing with when we talk about light's speed limit, except instead of water, we're talking about the fabric of space and time itself. But before we can truly understand why light moves at exactly 299,792,458 meters per second and not a whisker faster, we need to take a step back and explore what light actually is. For most of human history, this question sparked fierce debates among the brightest minds. Was light made of particles, like tiny invisible bullets shooting through space, or was it more like a wave, rippling through some mysterious medium? The ancient Greeks had their theories, of course. Some believed our eyes emitted rays that allowed us to see, which sounds amusing now but made perfect sense to people trying to understand vision without modern tools. Others proposed that objects themselves emitted something that traveled to our eyes. The Euclid and Ptolemy developed sophisticated theories about vision and light, though they were working with limited understanding of what light truly was. Fast forward to the 17th century, and we encounter two towering figures whose ideas would clash for decades. Sir Isaac Newton, whose name you probably recognize from that Apple story, was convinced light consisted of tiny particles he called corpuscles. These particles, he reasoned, traveled in straight lines and could explain why light cast sharp shadows and why it reflected off mirrors at predictable angles. Newton's reputation was so immense that his particle theory dominated scientific thinking for over a century. But there was another brilliant mind working on the same problem. Christian Huygens, a Dutch physicist and mathematician, proposed something quite different. He suggested light behaved like waves rippling through space. Huygens could explain many phenomena Newton's particles couldn't handle as elegantly, such as why light bends when it passes through different materials, a phenomenon we call refraction. The wave versus particle debate might seem like ancient history, but it's actually central to understanding light's speed limit. Here's why. If light was simply particles flying through empty space, there would be no inherent reason they couldn't go faster with more energy, just like a baseball thrown harder travels faster. But waves are different creatures entirely. Think about sound waves for a moment. When you speak, your vocal cords create vibrations that push and pull air molecules. These pressure waves travel through the air at a specific speed, roughly 343 meters per second at room temperature. Crucially, this speed doesn't depend on how loudly you shout. Screaming doesn't make sound waves travel faster through the air. It just makes them carry more energy, which we perceive as increased volume. The speed of sound through air is determined by the properties of air itself, things like its density and how easily it compresses. Different materials conduct sound at different speeds. Sound travels faster through water than air, and faster still through steel. But in each material, there's a characteristic speed that depends on the medium's physical properties, not on how much energy you put into creating the sound. This insight was revolutionary when applied to light. If light travels as waves, What medium is it waving through? This question led 19th century physicists to propose something called the luminiferous ether, an invisible substance that supposedly filled all of space and allowed light waves to propagate. They imagined this ether as incredibly rigid yet massless, permeating everything from the emptiest regions of space to the inside of solid matter. The ether seemed necessary because every wave scientists had encountered needed a medium. Ocean waves need water, sound waves need air, or some other material. Earthquake waves need solid rock. It seemed logical that light waves would need something too. Scientists spent decades trying to detect and measure the properties of this mysterious ether. But here's where the story takes a fascinating turn. Two American physicists, Albert Michelson and Edward Morley, designed an incredibly clever experiment in 1887 to detect Earth's motion through the ether. Their reasoning was straightforward. If Earth moves through this ether as it orbits the Sun, then light should appear to travel at different speeds, depending on whether it's moving with or against Earth's motion through the ether, just like how a swimmer's effective speed changes when swimming with or against a current. Their experiment was a masterpiece of precision. They used an interferometer, a device that splits a light beam, sends the pieces in perpendicular directions, then recombines them. If Earth were moving through the ether, the light traveling in the direction of Earth's motion should take a slightly different time to complete its journey compared to light traveling perpendicular to that motion. When the beams recombined, this tiny time difference would show up as a shift in the interference pattern. The result? Nothing. Absolutely nothing. No matter how they oriented their apparatus, no matter what time of year they conducted the experiment, they found no evidence whatsoever that Earth's motion affected the speed of light. This non-result was one of the most important negative results in the history of science. It suggested something profound. Either the ether didn't exist, or light's behavior was far stranger than anyone had imagined. This puzzling result sat uncomfortably in the scientific community for nearly 2 decades. Various explanations were proposed, including the idea that objects contract in the direction of their motion through the ether, perfectly compensating for the expected time differences. But these explanations felt forced, like trying to save a theory that nature was clearly rejecting. Then, in 1905, a young patent clerk in Switzerland published a paper that changed everything. Albert Einstein's special theory of relativity didn't try to explain away the Michelson-Morley result, it embraced it. Einstein proposed something radical. The speed of light in vacuum is the same for all observers, regardless of their motion. This wasn't just a strange property of light, it was a fundamental feature of space and time themselves. Let's pause for a moment and appreciate just how counterintuitive this idea is.
In everyday life, speeds are relative.
If you're walking forward in a moving train, your speed relative to the ground is your walking speed plus the train's speed. If you're walking backward in the train, you subtract your walking speed from the train's speed. This is basic common sense, confirmed by every experience we have with moving objects. But Einstein was saying that light doesn't follow these rules. If you shine a flashlight forward while moving in a car, someone standing on the roadside doesn't measure the light as traveling at the speed of light plus your car's speed. They measure it traveling at exactly the speed of light, the same speed you measure inside the car. This seems impossible, but decades of increasingly precise experiments have confirmed it beyond any doubt. The implications of this constant speed of light are staggering. If light always travels at the same speed regardless of the observer's motion, then something else must be flexible. Einstein realized that space and time themselves must stretch and compress to accommodate this cosmic speed limit. Moving clocks run slower, moving objects contract in length, and simultaneity becomes relative. These aren't just theoretical curiosities, they're practical realities that engineers must account for in technologies like GPS satellites. But we still haven't answered our original question. Why does light have this particular speed limit? Why is it roughly 300,000 kilometers per second and not some other value? To understand this, we need to dig deeper into what light actually is and how it relates to the fundamental structure of space and time. The key insight came from understanding that light is an electromagnetic wave. This realization emerged from the work of several brilliant physicists in the 19th century, culminating in James Clerk Maxwell's unified theory of electricity and magnetism. Maxwell discovered that electric and magnetic fields could propagate through space as waves, and when he calculated the speed of these electromagnetic waves, he got a number that matched the measured speed of light almost perfectly. This wasn't a coincidence. Light is electromagnetic radiation, the same phenomenon as radio waves, microwaves, X-rays, and gamma rays. The only difference between these various forms of electromagnetic radiation is their frequency, the number of wave cycles that pass a given point each second. Visible light occupies a tiny sliver of the electromagnetic spectrum, with red light having lower frequencies and blue light having higher frequencies. All electromagnetic waves, regardless of their frequency, travel at the same speed in vacuum. Radio waves from distant galaxies, the light from your reading lamp, and the gamma rays from nuclear decay all propagate at exactly 299,792,458 meters per second through empty space. This universal speed is built into the fundamental equations that describe electromagnetic fields. But why this specific speed? The answer lies in the properties of space itself. Just as the speed of sound through air depends on air's density and compressibility, the speed of electromagnetic waves through vacuum depends on the electromagnetic properties of space. These properties are described by two fundamental constants: the electric permittivity and magnetic permeability of free space. Think of space as having a certain resistance to electric fields and a certain resistance to magnetic fields. These resistances determine how quickly electromagnetic disturbances can propagate. The speed of light emerges naturally from these fundamental properties of space, much like the speed of sound emerges from the fundamental properties of air. Now here's where things get really interesting. Einstein's special relativity reveals that this speed, the speed of light, isn't really about light at all. It's the speed at which space and time are woven together. It's the maximum speed at which any information or influence can travel through the universe. Light just happens to travel at this fundamental speed because photons, the particles of light, have no mass. You see, anything with mass can never reach the speed of light. As objects with mass approach light speed, their energy requirements become infinite. It would take infinite energy to accelerate even a single electron to light speed, much less anything larger. This isn't a technological limitation. It's a fundamental feature of the universe. Only massless particles, like photons, can travel at the cosmic speed limit. This brings us to a profound realization. The speed of light is really the speed of space-time itself. It's the rate at which cause and effect can propagate through the universe. When you flip a light switch, the electromagnetic signal travels down the wire at nearly light speed. When gravitational waves ripple through space, they travel at exactly light speed. When quantum entangled particles influence each other, the correlations respect the light speed limit for any observable effects. But let's step back and think about what this means for our everyday experience. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. This means that when you look at the sun, you're seeing it as it was over 8 minutes ago, not as it is right now. The sun could theoretically disappear right now, and we wouldn't know about it for more than 8 minutes. We would continue to receive its light and feel its gravitational pull until the last photons and gravitational waves it emitted reached us. This delay becomes more dramatic as we look deeper into space. Light from the nearest star besides our sun, Proxima Centauri, takes over 4 years to reach us. The Andromeda Galaxy, our nearest major galactic neighbor, appears to us as it was 2.5 million years ago. When we look at the most distant galaxies visible to our telescopes, we're seeing them as they were billions of years ago, when the universe was young and very different from today. In essence, astronomy is time travel. Every observation is a glimpse into the past, with more distant objects showing us progressively earlier chapters in cosmic history. The speed of light limit creates this cosmic time machine, allowing us to observe the universe's evolution directly. This finite speed of light also has practical implications for space exploration and communication. Signals from Mars can take anywhere from 4 to 24 minutes to reach Earth, depending on the planet's positions in their orbits. This means that controlling a rover on Mars in real time is impossible. Engineers must send commands and wait for responses, building intelligence into the rovers so they can operate autonomously during these communication delays. For missions to the outer solar system, the delays become even more pronounced. Signals from Voyager 1, now in interstellar space, take over 22 hours to reach Earth. By the time we receive data from the spacecraft and send new commands, nearly 2 full days have passed. This is why deep space missions require robust autonomous systems and careful long-term planning. But the speed of light limit affects more than just space missions. It fundamentally shapes how information can flow through the universe. No signal, no influence, no information can travel faster than light in vacuum. This creates what physicists call light cones, regions of spacetime that can be causally connected to any given event. Imagine you're sitting in a chair right now. There's a sphere of space around you, with a radius equal to the distance light could travel in, say 1 second. Nothing outside this sphere can influence you in the next second, and you can't influence anything outside this sphere within the next second. As time passes, this sphere of possible influence expands at light speed, defining the boundary between events that can be causally connected and those that cannot. This might seem abstract, but it has real consequences. The finite speed of light means that simultaneity is relative. Events that appear to happen at the same time for one observer might happen at different times for another observer moving relative to the first. There's no universal now that extends across space, no cosmic clock that all observers can agree on. This relativity of simultaneity emerges directly from the constant speed of light. If you and a friend are moving apart and you both flash lights at what you consider the same moment, each of you will measure the other's light as arriving at a different time than expected. The effects are tiny at everyday speeds, but they become significant as relative velocities approach a substantial fraction of light speed. These ideas revolutionized our understanding of time itself. Time isn't the steady universal flow that Newton imagined. It's flexible, stretching, and compressing based on motion and gravity. Moving clocks run slow compared to stationary ones, and clocks in strong gravitational fields run slow compared to those in weaker fields. These aren't just theoretical predictions, they're measurable effects that must be corrected for imprecision technologies. GPS satellites, orbiting high above Earth, where gravity is slightly weaker and moving at high speeds relative to the surface, experience time dilation effects. Their onboard clocks run fast compared to identical clocks on the ground by about 38 microseconds per day. This might sound negligible, but GPS accuracy depends on precise timing. Without correcting for relativistic effects, GPS systems would accumulate errors of several kilometers per day, making them useless for navigation. The constancy of light speed also reveals something beautiful about the structure of physical laws. The equations that describe electromagnetic fields are the same for all observers, regardless of their motion. This principle, called Lorentz invariance, is built into the fundamental architecture of physics. The speed of light emerges as the natural scale that converts between space and time measurements, revealing their deep unity. In Einstein's theory, space and time aren't separate entities, but aspects of a unified four-dimensional space-time. The speed of light is the conversion factor between spatial distances and temporal intervals, much like an exchange rate converts between different currencies. Moving through space requires moving through time, and the speed of light determines the precise trade-off between spatial and temporal motion. This brings us to one of the most profound insights in physics. Everything in the universe is always moving through space-time at exactly the speed of light. This statement might sound confusing at first, but let me explain. When you're sitting still, you're moving through time at maximum rate and not moving through space. When you start moving through space, you begin moving through time slightly more slowly. The faster you move through space, the slower you move through time, but your total motion through space-time always adds up to the speed of light. Photons represent the extreme case. They move through space at the maximum possible speed, which means they don't move through time at all. From a photon's perspective, if photons could have perspective, the journey from a distant star to your eye happens instantaneously. The photon is created and absorbed in the same instant of its own time, even if millions of years pass for everyone else. This interplay between space and time, mediated by the speed of light, creates some of the strangest phenomena in physics. Take time dilation, for instance. If you could travel at 90% of light speed to a distant star and back, you might experience only a few years during the journey while decades pass on Earth. This isn't science fiction. It's a direct consequence of the geometry of space-time and the universal speed limit. Similarly, length contraction means that objects appear shorter in the direction of their motion when observed by someone moving relative to them. A spacecraft traveling at near light speed would appear flattened to a stationary observer, while everything in the stationary frame would appear flattened to the spacecraft's passengers. These effects become more extreme as speeds approach the speed of light, ultimately becoming infinite at light speed itself, which is why massive objects can never reach that ultimate velocity. The energy requirements for acceleration provide another perspective on why light speed is a universal limit. As you accelerate an object with mass to higher and higher speeds, it becomes progressively more difficult to increase its velocity further. The object's inertia, its resistance to acceleration, increases as its speed approaches light speed. At 90% of light speed, an object has more than twice its rest mass worth of kinetic energy. At 99% of light speed, the kinetic energy is 7 times the rest mass energy. As you approach 100% of light speed, the energy requirement approaches infinity. This isn't because the object becomes more massive. Despite what you might have heard, the object's mass remains constant, but the relationship between energy and velocity becomes nonlinear at high speeds. Adding energy to a fast-moving object increases its velocity less and less efficiently as it approaches light speed. It's like trying to push a boulder up an increasingly steep hill. The same effort produces smaller and smaller gains in height. Only particles with zero rest mass, like photons, can travel at light speed. They don't gradually accelerate to this speed. They're created already traveling at light speed and can only travel at light speed. Photons can't slow down or speed up. They can only be absorbed or pass through transparent materials where they interact with atoms in complex ways that can slow their effective progress without changing their actual speed in empty space. This creates an interesting paradox for our understanding of light. In a vacuum, light travels at its maximum speed, but when light passes through materials like glass or water, it appears to slow down. What's really happening is that photons are being absorbed and re-emitted by atoms in the material, creating delays that make the overall progress slower, even though each individual photon still travels at light speed in the brief moments it exists between atoms. The refractive index of a material, which determines how much light bends when entering it, is directly related to how much the light appears to slow down in that material. Diamond has a high refractive index, meaning light travels much slower through diamond than through air, which is why diamonds are so brilliant and sparkly. The light bounces around inside, changing direction each time it encounters an internal surface. But even in the densest materials, light never actually travels slower than its fundamental speed limit in the brief moments it exists as photons between interactions. The apparent slowing is a collective effect of countless absorption and emission events, each individual step happening at full light speed. This distinction becomes important when we consider some exotic phenomena that can appear to exceed light speed. For instance, if you point a laser at the moon and sweep it quickly across the lunar surface, the spot of light can move across the moon faster than light speed, but no information or energy is actually traveling at that speed. It's just a pattern moving across space. The photons themselves are still traveling from the laser to the moon at normal light speed. Similarly, quantum entanglement can create correlations between distant particles that seem to violate light speed limits. When you measure one entangled particle, its partner instantly knows the result, no matter how far away it is. But this quantum connection can't be used to send information faster than light. The correlations are real and instantaneous, but they can't be harnessed for faster than light communication. These apparent violations of light speed limits highlight an important distinction in physics: the difference between the motion of matter and energy versus the motion of patterns and information. While matter, energy, and information are bound by light speed limits, patterns can sometimes appear to move faster without actually violating the fundamental constraints. Think about stadium waves at sporting events. The wave of standing fans can move around the stadium much faster than any individual person could run around the track, but no person is actually moving at the wave's speed. They're just standing up and sitting down in sequence. The wave is a pattern of coordinated behavior, not the motion of any physical object. Some of the most exotic predictions of modern physics push against the boundaries of the light speed limit in fascinating ways. Quantum field theory suggests that empty space isn't actually empty, but filled with virtual particles constantly popping into and out of existence. These virtual particles can appear to violate energy conservation for very brief moments, borrowing energy from the vacuum and paying it back so quickly that the violation can't be directly observed. The Heisenberg uncertainty principle allows these temporary violations because it forbids simultaneously knowing both a particle's energy and the exact time it exists. Virtual particles live in this gray area of quantum uncertainty, existing just long enough to mediate forces between real particles before disappearing back into the vacuum. But even these ghostly virtual particles respect the light speed limit in their own strange way. Wormholes, if they exist, might provide another apparent exception to light speed limits. These hypothetical tunnels through space-time could connect distant regions of the universe, potentially allowing travel between them faster than light could travel through normal space. But even wormhole travel wouldn't violate causality because the geometry of space-time itself would be curved in such extreme ways that the normal rules of distance and time wouldn't apply. However, most physicists believe that traversable wormholes would require exotic matter with negative energy density to remain stable, and such matter has never been observed. The universe seems to have built-in protections against causality violations, even in the most extreme theoretical scenarios. Another interesting aspect of light speed limit relates to the expansion of space itself. The universe is expanding, carrying distant galaxies away from us at ever-increasing speeds. Galaxies sufficiently far away are receding faster than light speed due to the expansion of space between us. This doesn't violate relativity, because the galaxies aren't moving through space faster than light. Space itself is expanding and carrying them along. This cosmological expansion creates a cosmic horizon beyond which we can never observe galaxies, no matter how long we wait or how powerful our telescopes become. Light from these distant galaxies is traveling toward us at light speed, but the expansion of space is carrying the galaxies away from us faster than their light can make progress in our direction. These galaxies exist beyond our observable universe, invisible not because they're too faint, but because their light can never reach us. The cosmic microwave background radiation provides a beautiful example of light that has been traveling toward us for almost the entire age of the universe. This ancient light was emitted when the universe was only about 380,000 years old, and has been journeying through expanding space ever since. We observe it now as microwave radiation because the expansion of space has stretched its wavelength, shifting it from visible light into the microwave portion of the electromagnetic spectrum. This cosmic background radiation fills all of space uniformly and provides a natural reference frame for the universe. If you could measure your motion relative to this background radiation, you would find a unique speed at which the radiation appears perfectly uniform in all directions. This is as close as we can get to an absolute reference frame, though it's still not the luminiferous ether that 19th century physicists imagined. The uniformity of this cosmic background radiation also provides strong evidence for cosmic inflation, a period of extremely rapid expansion in the universe's first fraction of a second. During inflation, space expanded much faster than light speed, stretching quantum fluctuations to cosmic scales and creating the tiny variations in density that would eventually grow into galaxies and larger structures. Even inflation doesn't violate light speed limits, because once again, space itself was expanding rather than matter moving through existing space. The boundary between the observable and unobservable universe is defined by regions that were too far apart during inflation for light signals to have connected them, even at the universe's beginning. These cosmological considerations bring us to one of the deepest questions in physics. Why does the universe seem fine-tuned for the existence of complexity and life? The speed of light is just one of many fundamental constants that appear to have just the right values to allow atoms, stars, planets, and ultimately life to exist. If light speed were much faster, the electromagnetic force would be much stronger, potentially preventing atoms from forming stable structures. If it were much slower, chemical reactions might proceed too slowly for complex biochemistry to develop. The delicate balance of forces in nature depends critically on the precise values of fundamental constants like the speed of light. Some physicists propose that we live in a multiverse, where different regions have different values of fundamental constants, and we naturally find ourselves in a region where the constants are compatible with our existence. Others suggest that the constants are related by deeper physical principles we haven't yet discovered. This remains one of the great open questions in theoretical physics. The speed of light also plays a crucial role in our understanding of black holes, among the most extreme objects in the universe. At a black hole's event horizon, the escape velocity equals the speed of light. This is the boundary beyond which nothing, not even light, can escape. The existence of this boundary emerges directly from the finite speed of light and the equivalence of mass and energy revealed by relativity. From the perspective of someone falling into a black hole, nothing particularly special happens when crossing the event horizon. They would continue falling toward the center at increasing speed, but from the perspective of someone watching from a safe distance, the falling person would appear to slow down and freeze at the event horizon, their image growing redder and dimmer as time dilation and gravitational redshift become extreme. This apparent paradox illustrates how the finite speed of light creates different experiences of time and causality for different observers. The person falling into the black hole experiences a normal passage of time during their final moments, while external observers see those same moments stretched out over an infinite duration. Black holes also emit Hawking radiation, a quantum effect that occurs near the event horizon. Virtual particle pairs that normally annihilate each other can be separated by the black hole's intense gravity, with one particle falling in while the other escapes. This process causes black holes to slowly evaporate, with smaller black holes evaporating faster than larger ones. The rate of Hawking radiation depends on the black hole's temperature, which is inversely related to its mass. Paradoxically, as a black hole loses mass through radiation, it becomes hotter and radiates faster, leading to runaway evaporation in its final moments. For a black hole with the mass of our Sun, this evaporation process would take longer than the current age of the universe by many orders of magnitude. The information paradox associated with black hole evaporation relates directly to the speed of light limit and causality. If information falls into a black hole, and the black hole eventually evaporates completely through Hawking radiation, what happens to that information? Quantum mechanics suggests information cannot be destroyed, but general relativity seems to predict that information falling past the event horizon is lost forever. Various solutions to this paradox have been proposed, including the idea that information is gradually leaked out through correlations in the Hawking radiation, or that black holes don't have true event horizons, but instead have firewalls that destroy anything attempting to cross them. Each proposed solution has implications for our understanding of space-time and the fundamental nature of information in the universe. The speed of light also governs the propagation of gravitational waves, ripples in space-time itself that travel at exactly light speed. When massive objects accelerate, particularly in binary systems where two objects orbit each other at high speeds, They create disturbances in the geometry of space and time that propagate outward like waves on a pond. These gravitational waves were predicted by Einstein's general relativity, but weren't directly detected until 2015, when the LIGO experiment observed waves from two merging black holes. The detection confirmed that gravity is indeed a manifestation of curved spacetime, and that disturbances in this geometry propagate at the speed of light, not instantaneously as Newton had assumed. The fact that gravitational waves travel at light speed reveals something profound about the nature of gravity. In Newton's theory, gravity was an instantaneous force between masses. If the sun suddenly disappeared, Earth would immediately stop orbiting and fly off in a straight line. But Einstein's theory predicts that we would continue orbiting for about 8 minutes after the sun disappeared, until the gravitational waves announcing its absence reached us. This finite propagation speed for gravitational effects means that gravity, like electromagnetism, is a local phenomenon. Masses curve the spacetime in their immediate vicinity, and this curvature propagates outward at light speed to influence distant objects. There's no spooky action at a distance, just local interactions that take time to spread their influence through space. The detection of gravitational waves has opened an entirely new window on the universe, allowing us to observe events that produce no electromagnetic radiation, black hole mergers, neutron star collisions, and potentially even the cosmic inflation that occurred in the universe's first moments might be detectable through their gravitational wave signatures. Multi-messenger astronomy, which combines gravitational wave detections with traditional electromagnetic observations, has already provided unprecedented insights into extreme astrophysical events. When two neutron stars merged in 2017, the event was observed simultaneously through gravitational waves and gamma rays, confirming that such mergers are sources of heavy elements like gold and platinum. The precision required to detect gravitational waves illustrates just how small the effects of spacetime curvature can be. LIGO can detect changes in distance smaller than 1/10,000th the width of a proton, achieved by measuring how gravitational waves slightly stretch and compress the paths of laser beams, traveling between mirrors separated by several kilometers. This incredible sensitivity is necessary because gravitational waves interact very weakly with matter, while electromagnetic waves can be absorbed, reflected, or scattered by materials they encounter. Gravitational waves pass through almost everything with minimal interaction. This makes them extremely difficult to detect, but also means they carry information from the most distant and ancient parts of the universe essentially unchanged. The cosmic microwave background provides electromagnetic information about the universe when it was 380,000 years old, but gravitational waves could potentially tell us about much earlier epochs, perhaps even the first moments after the Big Bang, when the universe was far too dense and hot for light to travel freely. Future gravitational wave detectors, both on Earth and in space, will probe different frequency ranges and achieve even greater sensitivity. The Laser Interferometer Space Antenna, planned for launch in the 2030s, will use 3 spacecraft separated by millions of kilometers to detect gravitational waves from massive black hole mergers and other low-frequency sources invisible to ground-based detectors. These technological marvels exist because we understand the speed of light and its role in the fundamental structure of space-time. Every precision measurement, every GPS satellite, every fiber optic communication system depends on our knowledge of how electromagnetic radiation propagates through space and matter. The speed of light connects the quantum mechanical world of atoms and molecules to the relativistic world of high speeds and strong gravitational fields. In quantum electrodynamics, the theory that describes how light interacts with charged particles, the speed of light appears as a fundamental parameter that determines the strength of electromagnetic interactions. The fine structure constant, one of the most precisely measured numbers in physics, is a dimensionless combination of the electron charge. Planck's constant and the speed of light. This constant determines how strongly atoms bind electrons and how readily they emit and absorb light. If its value were significantly different, atoms might not exist at all, or they might be so strongly bound that chemical reactions couldn't occur. Quantum field theory reveals that even empty space is filled with fluctuating electromagnetic fields that respect the speed of light limit. These zero-point fluctuations create measurable effects like the Casimir force, where two metal plates placed very close together in vacuum experience an attractive force due to the modification of vacuum fluctuations between them. The uncertainty principle ensures that these vacuum fluctuations can never be eliminated completely. Even at absolute zero temperature, when all thermal motion ceases, quantum fields continue to fluctuate with their minimum possible energy. These fluctuations propagate at light speed and contribute to phenomena ranging from the spontaneous emission of light by excited atoms to the Hawking radiation from black holes. Particle accelerators push the boundaries of our understanding by accelerating particles to speeds very close to light speed. The Large Hadron Collider accelerates protons to over 99.999999999999999999999999999999999999999999999999999. At these speeds, relativistic effects dominate every aspect of the particle's behavior. The time dilation experienced by these fast-moving particles allows unstable particles with very short lifetimes to travel much farther than they could at rest before decaying. Cosmic ray muons created in the upper atmosphere provide a natural example, living long enough to reach Earth's surface only because their high-speed motion dilates their lifetimes from our perspective. High-energy particle physics has revealed that the electromagnetic force is intimately connected to the weak nuclear force, the interaction responsible for certain types of radioactive decay. At very high energies, these forces merge into a single electro-weak interaction, suggesting that the speed of light might be connected to even deeper symmetries in the laws of physics. Grand unified theories attempt to merge the electromagnetic, weak, and strong nuclear forces into a single framework, potentially explaining why the speed of light has its particular value in terms of more fundamental principles. These theories remain speculative, but they suggest that the speed of light might not be an arbitrary constant, but rather a consequence of the universe's deepest mathematical structure. String theory, which attempts to describe all fundamental particles as vibrating strings in higher dimensional space, also incorporates the speed of light as a fundamental parameter. In string theory, the speed of light emerges from the geometry of the extra dimensions and the properties of the strings themselves. Different compactifications of these extra dimensions could, in principle, lead to different values of fundamental constants in different regions of a vast multiverse. But we don't need exotic theories to appreciate the profound role of light's speed limit in shaping our universe. The simple fact that light has a finite speed means that the universe has a history, that we can observe distant galaxies as they were in the past, and that information takes time to propagate from one place to another. Without this finite speed, causality would be meaningless. Every event would instantly affect every other event throughout the universe. There would be no sequence of cause and effect, no evolution of structure, no possibility for complexity to develop gradually over time. The universe would be static and boring, without the rich tapestry of phenomena we observe. The speed of light also determines the fundamental scale of atomic physics. The Bohr radius, the characteristic size of atoms, depends on the fine structure constant, which incorporates the speed of light. If light were much faster, atoms would be much smaller, and chemistry as we know it couldn't exist. If light were much slower, atoms might be too large and weakly bound to form stable molecules. This intimate connection between light speed and atomic structure means that every biological process, from photosynthesis in plants to neural signaling in your brain, depends critically on light having exactly the speed it does. Photosynthesis captures light energy with remarkable efficiency, partly because the molecular machinery has evolved to work with photons of specific energies that correspond to light speed and atomic properties. The chlorophyll molecules in plants absorb red and blue light while reflecting green, giving plants their characteristic color. This wavelength selectivity emerges from quantum mechanics, and the speed of light working together to determine how electrons behave in complex molecules change the speed of light significantly, and photosynthesis might become impossible. Even more remarkably, vision itself depends on light speed in subtle ways. When light hits the rhodopsin molecules in your retina, it triggers a cascade of molecular changes that ultimately create the electrical signals your brain interprets as images. The timing of these molecular processes is calibrated to work with light of the specific energy and wavelength ranges that reach Earth's surface after filtering through our atmosphere. The fact that we can see at all is partly due to the transparency of our atmosphere to visible light. Water vapor, oxygen, and other atmospheric gases interact with electromagnetic radiation in ways that depend on light speed and the quantum mechanical properties of molecules. Our eyes evolved to detect the wavelengths that penetrate most effectively through air and water, creating a biological system perfectly matched to the optical properties of our environment. This brings us to an interesting philosophical question. Is the speed of light truly fundamental, or is it an emergent property of something even deeper? Some theories suggest that space and time themselves might not be fundamental, but could emerge from more basic entities, perhaps discrete bits of information, or quantum entanglement networks that operate below the scale, where space-time appears smooth and continuous. In these approaches, the speed of light would be like the speed of sound in a material, an emergent property that appears when you average over many microscopic interactions. The individual quantum events might not respect a speed limit, but the collective behavior would naturally produce the light speed limit we observe at larger scales. Loop quantum gravity, for instance, proposes that space and time are made of discrete loops at the Planck scale, about 10 to the power of minus 35 meters. At this scale, the smooth spacetime of Einstein's relativity would break down into a foamy quantum structure where the usual concepts of distance and duration might not apply. The speed of light would emerge as a statistical property of how information propagates through this quantum foam. String theory suggests something similar but different. In string theory, the fundamental entities are one-dimensional strings vibrating in higher dimensional space. The speed of light in our familiar three-dimensional space would be determined by how these strings interact and how the extra dimensions are compactified or curled up on scales too small to observe directly. But even if light speed is emergent rather than fundamental, it still plays the same crucial role in organizing the universe we experience. Whether it arises from deeper principles or represents a truly basic feature of reality, the cosmic speed limit shapes everything from the behavior of subatomic particles to the large-scale structure of the universe. One of the most beautiful aspects of physics is how the same principles apply across vastly different scales. The speed of light governs both the emission of radiation by a single accelerating electron and the propagation of gravitational waves from merging galaxies. It determines both the structure of atoms and the fate of the universe. Speaking of the universe's fate, the speed of light plays a crucial role in cosmological evolution. The expansion of space carries distant regions beyond each other's light horizons, effectively disconnecting them causally. What happens in one region can no longer influence what happens in sufficiently distant regions, leading to the gradual isolation of different parts of the universe. As the universe continues to expand and cool, regions that can currently communicate through light signals will eventually lose contact forever. The observable universe will paradoxically contain fewer and fewer galaxies over cosmic time, not because they're destroyed, but because their light can no longer reach us through the ever-expanding space between us. This cosmic isolation has profound implications for the far future. In the extremely distant future, long after stars have exhausted their fuel and died, the universe will become a cold, dark place, where isolated black holes slowly evaporate through Hawking radiation. Even this process respects the speed of light limit, with information about the black hole's contents potentially encoded in the correlations between Hawking radiation photons. The ultimate fate of information in an expanding universe remains one of the deepest puzzles in physics. If space continues expanding exponentially, as current observations suggest, then information processing will become increasingly difficult as physical systems become isolated from each other. The speed of light limit ensures that computation requires physical resources, and these resources become increasingly scarce in an eternally expanding universe. Yet even in this far future scenario, the speed of light continues to play a fundamental role. Any remaining structures, whether they're conscious observers or just random fluctuations in quantum fields, would still be bound by the same light speed limit that governs physics today. The laws of relativity would remain unchanged even in a universe vastly different from our current one. This universality of physical laws across time and space is one of the most remarkable features of our universe. The speed of light measured in a laboratory today is the same as the speed of light that governed the universe's behavior billions of years ago and will continue to govern it billions of years in the future. This constancy allows us to understand distant astronomical phenomena using the same physical principles we can test on Earth. The constancy of light speed also enables precise tests of fundamental physics using astronomical observations. By comparing the spectra of light from distant quasars with laboratory measurements, physicists can test whether fundamental constants like the fine structure constant have changed over cosmic time. So far, these tests show remarkable stability, with any changes being smaller than a few parts in a million over billions of years. The stability suggests that the speed of light and related constants are indeed fundamental features of reality rather than accidents of our particular cosmic epoch. If these constants were gradually changing, we would expect to see evidence in the spectra of ancient light, but the universe appears to have maintained the same physical laws throughout its observable history. The precision of these measurements is truly astounding. When we analyze light that has traveled for billions of years from distant quasars, we can measure tiny shifts in spectral lines that would indicate changes in fundamental constants. The fact that these measurements show such remarkable consistency tells us that the universe operates according to stable, mathematical laws rather than chaotic, changing rules. This mathematical nature of physical laws is perhaps the deepest mystery of all. Why should the universe be comprehensible to mathematical analysis? Why do simple equations like Maxwell's laws of electromagnetism capture the behavior of light with such precision? The speed of light appears in these equations not as an arbitrary parameter, but as a natural consequence of the mathematical structure itself. Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in the natural sciences, noting how mathematical concepts developed for pure abstract reasons often turn out to describe physical phenomena with startling accuracy. The speed of light is a perfect example. It emerges naturally from the mathematical structure of electromagnetic theory, yet it governs real physical phenomena throughout the universe. This effectiveness of mathematics in describing nature suggests a deep connection between the structure of mathematics and the structure of physical reality. Some physicists and philosophers argue that mathematics doesn't just describe the universe, but actually is the universe in some fundamental sense. In this view, the speed of light isn't just described by mathematical equations, it literally is a mathematical relationship made manifest in physical reality. Whether or not you accept such a radical view, the mathematical precision with which we can describe light's behavior is remarkable. We can predict the path of a laser beam, the interference pattern from a double-slit experiment, or the spectrum of light from a distant star using the same mathematical framework. This universality suggests that we've discovered something truly fundamental about the nature of reality. The speed of light also connects to one of the most profound questions in science, the nature of time itself. In relativity, time is not separate from space, but forms part of a unified space-time continuum. The speed of light is the conversion factor that relates space and time measurements, much like an exchange rate relates different currencies. This view of time as a dimension similar to space has radical implications. It suggests that past, present, and future all exist equally in a four-dimensional space-time block, with our perception of flowing time being an illusion created by our particular perspective as conscious observers. The speed of light defines the geometry of this block universe, determining which events can be causally connected and which cannot. In this block universe picture, Every moment of your life, past and future, exists eternally in space-time. You're not moving through time so much as existing as an extended four-dimensional object with temporal as well as spatial dimensions. The speed of light determines the shape of this four-dimensional existence, defining the light cones that separate your past from your future. This static view of time seems to conflict with our immediate experience of moment-to-moment change and free choice, yet it emerges naturally from the mathematical structure of relativity theory and has been confirmed by countless experiments. The resolution of this apparent paradox remains one of the deep puzzles in understanding the nature of consciousness and its relationship to physical reality. Perhaps our sense of temporal flow emerges from the way information is processed in complex systems like brains. The speed of light limit ensures that information processing takes time and creates natural sequences of cause and effect. Even in a block universe where all moments exist equally, conscious observers might naturally experience these moments in a specific order determined by the causal structure defined by light speed limits. The thermodynamic arrow of time provides another perspective on this puzzle. Entropy, the measure of disorder in a system, tends to increase over time in isolated systems. This creates a natural direction to time even in a universe where past, present, and future all exist equally. The speed of light plays a role here too, as it determines how quickly thermal equilibrium can be established between different regions of space. Heat flows from hot objects to cold objects, but this process takes time because energy must travel at finite speed from one location to another. If energy could be transferred instantaneously, thermal equilibrium would be established immediately throughout any connected system. The finite speed of light ensures that thermal processes unfold gradually, creating the familiar arrow of time we experience in everyday life. This connection between light speed and thermodynamics extends to the deepest levels of physics. Black hole thermodynamics, for instance, reveals that black holes have temperature and entropy that depend on their surface area rather than their volume. This unusual relationship emerges from the finite speed of light and the properties of event horizons. The holographic principle, inspired by black hole physics, suggests that all the information in a volume of space can be encoded on its boundary surface. This principle has profound implications for our understanding of space, time, and information. If true, it means that three-dimensional reality might be a projection from information stored on a two-dimensional surface, much like a hologram encodes three-dimensional images on flat film. The speed of light plays a crucial role in holographic theories because it determines how quickly information can be transmitted between different parts of the boundary surface. The bound on information transmission speed creates constraints on how much information can be processed in any given region of space-time, leading to fundamental limits on computation and complexity. These ideas connect to current research in quantum computing and quantum information theory. Quantum computers harness the strange properties of quantum mechanics to perform certain calculations exponentially faster than classical computers. But even quantum computers are bound by relativistic limits. They cannot transmit information faster than light or violate causality. The no-communication theorem in quantum mechanics ensures that while quantum entanglement creates instant correlations between distant particles, these correlations cannot be used to send messages faster than light. The quantum advantage in computation comes from parallel processing of quantum superpositions, not from bypassing relativistic constraints. This interplay between quantum mechanics and relativity continues to generate new insights into the fundamental nature of reality. Quantum field theory, which combines these two frameworks, predicts phenomena like virtual particles and vacuum fluctuations that have been confirmed experimentally. The speed of light appears throughout quantum field theory as the parameter that determines how quantum fields propagate through space-time. One of the most remarkable predictions of quantum field theory is that empty space is not actually empty, but filled with fluctuating fields that can produce measurable effects. The Casimir effect, where two metal plates in vacuum experience an attractive force, demonstrates that these quantum fluctuations are real physical phenomena with observable consequences. These vacuum fluctuations also contribute to the anomalous magnetic moment of the electron, one of the most precisely measured quantities in physics. The theoretical calculation of this quantity requires summing over infinitely many quantum processes, each involving virtual particles that respect the speed of light limit. The agreement between theory and experiment to more than 10 decimal places represents one of the greatest triumphs of theoretical physics. The precision of such calculations depends critically on our understanding of how electromagnetic fields propagate at light speed. Any deviation from the expected speed of light would show up as discrepancies in these precise measurements. The fact that theory and experiment agree so well provides strong evidence that our understanding of light's behavior is essentially correct. This level of precision also allows us to search for new physics beyond our current theories. If exotic particles or interactions exist that modify electromagnetic propagation in subtle ways, they might show up as tiny discrepancies in precision measurements. The speed of light serves as a standard against which all other phenomena can be measured. Dark matter and dark energy, the mysterious components that make up most of the universe's mass and energy, interact with ordinary matter primarily through gravity rather than electromagnetic forces. This means they don't directly affect the speed of light, but their gravitational effects can bend light rays and create gravitational lensing effects that we can observe. Gravitational lensing occurs when the curved spacetime around massive objects acts like a lens, focusing light from distant sources. This effect, predicted by Einstein's general relativity, has been observed countless times and provides a powerful tool for studying both the lensing objects and the distant sources whose light is being focused. The fact that gravitational lensing works exactly as relativity predicts provides strong evidence that our understanding of spacetime geometry is correct. Light follows the straightest possible paths through curved spacetime, and these paths can be calculated precisely using the mathematical framework of general relativity. Some of the most spectacular examples of gravitational lensing occur when light from distant galaxies is focused by intervening galaxy clusters. The cluster's gravity can create multiple images of the same background galaxy stretched into arcs and rings around the cluster. These Einstein rings provide a dramatic demonstration of how mass and energy curve spacetime. The time delays between different images in gravitational lensing systems can be used to measure cosmological distances and the expansion rate of the universe. Light traveling along different paths through the curved spacetime takes different amounts of time to reach us, and these time differences depend on the geometry of the universe and the distribution of matter and energy within it. These measurements have contributed to our discovery that the universe's expansion is accelerating, driven by dark energy that makes up about 68% of the universe's total energy density. Dark energy appears to act like a cosmological constant, a uniform energy density that doesn't dilute as space expands. Its nature remains one of the greatest mysteries in modern physics. The acceleration of cosmic expansion has profound implications for the future of the universe and the ultimate fate of information and complexity. If dark energy continues to dominate cosmic evolution, the universe will expand exponentially fast in the far future, eventually separating all structures beyond their mutual light horizons. This scenario, sometimes called the Big Rip, would tear apart all bound structures, from galaxy clusters down to individual atoms, as the expansion rate accelerates without limit. Even this extreme scenario would unfold according to the laws of relativity, with the speed of light continuing to govern causal relationships until the very end. But we're getting ahead of ourselves, diving into speculative cosmology, when there's still so much beauty in the here and now. Applications of light's speed limit. Consider fiber optic communication, the technology that carries most of the world's internet traffic. These systems work by sending pulses of light through glass fibers, taking advantage of light's high speed and the fact that glass can be made extremely transparent to certain wavelengths. The information capacity of fiber optic systems is fundamentally limited by the speed of light and the physics of electromagnetic propagation. Engineers must carefully account for dispersion effects that cause different wavelengths of light to travel at slightly different speeds through the fiber, potentially scrambling the encoded information. Modern fiber optic systems use sophisticated techniques to overcome these limitations, including wavelength division multiplexing that sends many separate data streams at different colors through the same fiber. Each color channel can carry enormous amounts of information, but the total data rate is still limited by how quickly light can propagate and how precisely engineers can control its properties. The global internet depends entirely on these light-based communication systems. When you stream a video or send a message across the world, the information travels as pulses of light racing through undersea cables at nearly the speed of light in glass, which is about 2/3 the speed of light in vacuum. The slight delay you sometimes notice in international communications is often due to this finite propagation speed rather than processing delays. Satellite communication systems face even more obvious speed of light constraints. Geostationary satellites orbit at about 36,000 kilometers above Earth's equator, which means radio signals take about 0.24 seconds to travel from Earth to the satellite and back. This round-trip delay is noticeable in satellite phone conversations and creates challenges for real-time applications like online gaming or video conferencing. Low Earth orbit satellite constellations, like those being deployed for global internet service, orbit much closer to Earth and therefore have much lower communication delays. But they require more complex systems to hand off connections as satellites move across the sky, and they still face the fundamental constraint that information cannot travel faster than light. These practical limitations remind us that the speed of light is not just an abstract physical constant, but a real constraint that affects technology and daily life. GPS systems must account for relativistic effects on satellite clocks. Computer processors are limited by how quickly signals can propagate across their circuitry, and even the size of computer chips is constrained by the need to minimize light travel delays. As computer processors become faster and more complex, the speed of light becomes an increasingly important design constraint. Modern processors use numerous tricks to work around these limitations, including predictive algorithms that guess what data will be needed next, and parallel processing that performs multiple calculations simultaneously. Quantum computers face similar constraints, despite their ability to harness quantum superposition and entanglement. The quantum states must be manipulated using classical control systems that are bound by relativistic limits, and the final readout of quantum computations must be performed using conventional electronics that respect light speed constraints. The development of quantum internet systems, which would use quantum entanglement to create ultra-secure communication channels, must also work within relativistic constraints. While quantum correlations can be established instantaneously between distant particles, using these correlations for communication still requires classical information transmission at light speed or below. These emerging technologies highlight how the speed of light continues to be relevant even as we push into new frontiers of physics and engineering. No matter how exotic our technologies become, they must still respect the fundamental constraints imposed by the structure of space-time. This brings us back to one of our central themes. The speed of light is not just about light, but about the fundamental structure of reality itself. It determines how space and time are related, how cause and effect propagate through the universe, and how information and energy can flow from one location to another. Understanding light's speed limit has practical applications, from designing communication systems to navigating spacecraft, but it also provides deep insights into the nature of existence itself. The universe is not a collection of isolated objects, but a unified whole, where every part can potentially influence every other part, given enough time for signals to propagate at light speed. This cosmic interconnectedness creates a kind of universal community where events in distant galaxies can eventually affect what happens here on Earth, and vice versa. The light from dying stars becomes part of the cosmic background that influences the formation of new stars and planets. The heavy elements forged in stellar cores are dispersed by supernova explosions and incorporated into new worlds where life might arise. Even the biological elements in your body were created in this cosmic recycling process. The carbon in your muscles, the oxygen in your lungs, the iron in your blood, All were forged in the nuclear furnaces of massive stars and distributed through space when those stars exploded. The speed of light determined how long it took for these elements to travel from their stellar birthplaces to the molecular clouds where our solar system eventually formed. In a very real sense, you are made of starlight, not just metaphorically but literally. The atoms in your body once existed inside stars, where they were heated to millions of degrees and subjected to pressures millions of times greater than Earth's atmosphere. The energy that powered their creation came from nuclear fusion, the same process that makes stars shine by converting mass into energy according to Einstein's famous equation. This stellar nucleosynthesis process proceeds at rates determined partly by the speed of light, which governs how quickly energy can escape from stellar cores, and how electromagnetic radiation pressure balances against gravitational collapse. Change the speed of light significantly, and stars might burn too quickly or too slowly to create the stable conditions necessary for element formation. The delicate balance that allows stars to shine steadily for billions of years depends on numerous physical constants working together in harmony. The speed of light helps determine the opacity of stellar matter to radiation, which affects how energy flows from the core to the surface. This energy transport is crucial for maintaining the temperature and pressure gradients that keep stars stable. When massive stars finally exhaust their nuclear fuel, they collapse catastrophically in supernova explosions that can briefly outshine entire galaxies. These explosions are powered by gravitational energy release and nuclear reactions that create elements heavier than iron. The shock waves from supernova trigger the formation of new stars in nearby molecular clouds, continuing the cycle of stellar birth, death, and rebirth. The expanding shock waves from supernovae also create some of the most spectacular objects in the universe, supernova remnants that can shine in radio waves and X-rays for thousands of years after the original explosion. These remnants provide natural laboratories for studying how matter behaves under extreme conditions, with magnetic fields millions of times stronger than Earth's and particles accelerated to nearly light speed. Cosmic rays, high-energy particles that constantly bombard Earth from space, are created in these extreme environments. Most cosmic rays are protons accelerated to enormous energies by magnetic fields in supernova remnants and other astrophysical accelerators. The highest energy cosmic rays carry more energy than particles in our most powerful accelerators, yet they're just individual protons traveling at speeds very close to the speed of light. When these ultra-high energy cosmic rays hit Earth's atmosphere, they create cascades of secondary particles that can be detected by ground-based observatories. The fact that we can observe these particles at all depends on relativistic time dilation effects. The high-speed particles live much longer than they would at rest, allowing them to survive the journey through our atmosphere. The study of cosmic rays provides insights into both fundamental particle physics and astrophysical processes occurring throughout the universe. The highest energy events involve particles with energies so extreme that they probe physics beyond what we can achieve in terrestrial laboratories. Yet even these exotic phenomena respect the speed of light limit and the principles of relativity. Neutrinos represent another fascinating aspect of high-speed particle physics. These nearly massless particles interact so weakly with matter that they can travel through the entire Earth with only a tiny chance of being absorbed or scattered. Trillions of neutrinos from the Sun pass through your body every second without you noticing. Neutrinos travel at speeds extremely close to, but not quite equal to, the speed of light. The tiny difference between their speed and light speed depends on their small but non-zero mass. In 2011, an experiment called Opera initially reported that neutrinos appeared to arrive slightly faster than light speed, causing great excitement and controversy in the physics community. The faster-than-light neutrino result was eventually traced to a loose cable connection that introduced systematic errors in the timing measurements. This incident highlights how seriously physicists take potential violations of relativistic speed limits. Any confirmed faster-than-light signal would require a complete revolution in our understanding of physics. The corrected measurements showed that neutrinos do indeed travel slightly slower than light, consistent with their having small masses. This mass difference between different types of neutrinos creates the phenomenon of neutrino oscillations, where neutrinos can change from one type to another as they travel through space. Neutrino oscillations provide one of the few direct probes of physics beyond the standard model of particle physics. The fact that neutrinos have mass was not predicted by the original formulation of the standard model, and understanding neutrino properties remains an active area of research, with implications for both particle physics and cosmology. The speed of neutrinos, while slightly less than light speed, is still fast enough that neutrinos from distant supernovae can reach Earth hours before the light from the same explosions. This happens because neutrinos can escape from the collapsing stellar core immediately, while light must slowly work its way out through the dense stellar envelope. Supernova 1987 provided a dramatic demonstration of this effect. Neutrino detectors on Earth observed the neutrino burst from this stellar explosion about 3 hours before the light became visible to telescopes. This early warning system gave astronomers time to point their instruments at the right location and observe the supernova explosion as it unfolded. Future neutrino observatories will provide even earlier warnings of stellar explosions and other high-energy astrophysical events. By detecting neutrinos from collapsing stars throughout our galaxy and nearby galaxies, these systems could alert astronomers to observe rare phenomena like neutron star mergers or black hole formation events. The fact that neutrinos can carry information across cosmic distances without significant interaction makes them valuable messengers from the most extreme environments in the universe. While electromagnetic radiation can be absorbed or scattered by intervening matter, neutrinos travel essentially unimpeded from their sources to our detectors. IceCube, a neutrino observatory built into the Antarctic ice sheet, detects high-energy neutrinos from distant astronomical sources by observing the faint flashes of light they create when they finally do interact with matter. These interactions are extremely rare, requiring huge volumes of detection medium to catch even a few events per year. The neutrinos detected by IceCube have been traced to their sources in distant galaxies, providing a new way to study active galactic nuclei and other high-energy phenomena. These observations complement traditional electromagnetic astronomy and gravitational wave astronomy to create a more complete picture of the universe's most energetic processes. Multi-messenger astronomy, which combines observations of electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays from the same sources, is revolutionizing our understanding of extreme astrophysical events. Each type of messenger travels at or near the speed of light, but interacts differently with matter, providing complementary information about the same physical processes. The 2017 observation of gravitational waves and electromagnetic radiation from a neutron star merger demonstrated the power of this approach. The gravitational waves revealed details about the masses and orbital dynamics of the merging objects, while the electromagnetic observations showed how heavy elements were created and dispersed by the collision. Future multi-messenger observations will provide even more detailed studies of these extreme events. Advanced detectors with greater sensitivity and wider coverage will catch more events and provide more precise measurements of their properties. The speed of light ensures that signals from the same event arrive at Earth within a narrow time window, allowing coordinated observations across different messenger types. These observations also provide tests of fundamental physics under conditions impossible to replicate on Earth. Neutron star mergers involve matter at nuclear density, magnetic fields stronger than any laboratory can produce, and gravitational fields so strong that they significantly warp space-time. The fact that all our messenger types arrive consistent with light speed propagation confirms that relativity works even in these extreme environments. Speaking of extreme environments, let's consider what happens near black holes, where gravity becomes so strong that it significantly affects the passage of time and the behavior of light. The event horizon of a black hole is defined as the surface where the escape velocity equals the speed of light. Nothing inside this boundary can send signals to the outside universe. But the physics becomes very strange near event horizons. Due to gravitational time dilation, time appears to slow down for objects approaching a black hole when viewed from a safe distance. From the perspective of someone falling into the black hole, however, time passes normally during their final journey. This creates a fascinating paradox. An outside observer would see a falling object slow down and freeze at the event horizon, appearing to hover there forever as its image becomes increasingly redshifted and dim. But from the falling object's perspective, it passes through the event horizon in finite time and continues falling toward the center. Both perspectives are correct within their own reference frames, illustrating how the finite speed of light creates different experiences of time and causality for different observers. The resolution involves understanding that the event horizon is not a physical surface, but rather a boundary in space-time defined by light rays that can just barely escape to infinity. Hawking radiation adds another layer of complexity to black hole physics. Quantum effects near the event horizon can create particle pairs, where one member falls into the black hole while the other escapes. This process causes black holes to slowly evaporate, with smaller black holes evaporating faster than larger ones. The Hawking radiation carries information about the black hole's properties, but it's scrambled in complex ways that make it extremely difficult to decode. This creates the black hole information paradox, one of the deepest puzzles in theoretical physics. If information falling into a black hole is eventually returned through Hawking radiation, how is it encoded in the outgoing particles? Various solutions to this paradox have been proposed, including the idea that the event horizon is not smooth, but contains a firewall that destroys anything attempting to cross it, or that information is gradually leaked out through subtle correlations in the Hawking radiation. Each proposed solution has profound implications for our understanding of quantum mechanics, gravity, and the nature of information itself. The black hole information paradox highlights the tension between quantum mechanics, which demands that information be preserved, and general relativity, which suggests that information falling past an event horizon is lost forever. Resolving this paradox may require a theory of quantum gravity that unifies these two fundamental frameworks. String theory and loop quantum gravity represent two leading approaches to developing such a unified theory. Both predict modifications to the physics of black holes that could resolve the information paradox, but these modifications occur at scales so small and energies so high that they're currently impossible to test directly. The speed of light plays a crucial role in both approaches. In string theory, it emerges from the dynamics of vibrating strings in higher dimensional space. In loop quantum gravity, it represents the speed at which information can propagate through the discrete quantum geometry of space and time. These theories suggest that space and time themselves might not be continuous, but made of discrete components at the smallest scales. The Planck length, about 10 to the power of minus 35 meters, represents the scale where quantum effects on gravity become important. At this scale, the familiar concepts of distance and duration might break down completely. If space and time are discrete at the Planck scale, then the speed of light might represent the rate at which information can hop from one discrete spacetime element to another. This would make light speed a fundamental property of the quantum geometry of spacetime, rather than a property of electromagnetic fields propagating through continuous space. These ideas remain highly speculative, but they illustrate how the speed of light connects to the deepest questions in theoretical physics, whether space and time are continuous or discrete, whether information is truly conserved in all circumstances, and whether our current theories represent the final word on the nature of reality. All of these questions involve the speed of light in fundamental ways. The beauty of physics lies partly in how simple principles like the constancy of light speed lead to profound insights about the nature of reality. From this one principle, Einstein derived the entire structure of special relativity, revolutionizing our understanding of space, time, matter, and energy. The mathematical elegance of relativity theory, where complex phenomena emerge from simple geometric principles, suggests that we've discovered something truly fundamental about the universe's structure. The speed of light appears not as an arbitrary constant, but as a natural feature of the geometry of spacetime itself. This geometric interpretation of physics extends beyond relativity to other areas of theoretical physics. Gauge theories, which describe the electromagnetic, weak, and strong nuclear forces, can be understood as theories of curved spaces in abstract mathematical dimensions. The speed of light appears in these theories as a fundamental parameter that determines how these abstract geometries relate to physical phenomena. The Standard Model of particle physics, our most successful theory of fundamental particles and forces, incorporates the speed of light as a basic parameter that appears throughout its mathematical structure. Every calculation in particle physics, from predicting the outcomes of collider experiments to understanding how stars shine, depends on this fundamental constant. Yet despite its success, the Standard Model leaves many questions unanswered. Why do particles have the masses they do? Why are there 3 generations of matter particles? Why is the universe made of matter rather than antimatter? The speed of light appears in all these mysteries, suggesting that understanding its ultimate origin might be key to solving these puzzles. Beyond the Standard Model physics, theories like supersymmetry and extra dimensions continue to incorporate the speed of light as a fundamental parameter. These theories predict new particles and phenomena that could be discovered in future experiments, but they all respect the basic structure of relativity and the fundamental role of light's speed limit. The search for physics beyond the Standard Model continues at particle accelerators around the world. The Large Hadron Collider has discovered the Higgs boson and continues to probe higher energies and rarer processes. Future accelerators will push even deeper into unexplored territory, always constrained by the fundamental limits imposed by the speed of light. Even if we discover new physics beyond our current theories, it will almost certainly incorporate the speed of light as a fundamental parameter. The evidence for relativity is so overwhelming, and its predictions so precise, that any new theory must reduce to relativity in the appropriate limits. This suggests that the speed of light represents a truly fundamental aspect of reality, not just a feature of our current theories, but a basic property of the universe that any complete description must incorporate. Whether we eventually develop theories of quantum gravity, discover extra dimensions, or encounter completely unexpected phenomena, the speed of light will likely remain a cornerstone of our understanding. As we continue to explore the universe through ever more sophisticated observations and experiments, the speed of light serves as both a tool for investigation and a fundamental constraint on what we can discover. It determines how quickly information can travel from distant objects to our telescopes, how precisely we can measure cosmic distances, and how directly we can test the predictions of our theories. The James Webb Space Telescope, humanity's most powerful space observatory, uses the finite speed of light to observe the universe as it was billions of years ago. By looking deeper into space, it looks further back in time, providing direct observations of how galaxies, stars, and planetary systems formed in the early universe. These observations rely on our precise understanding of how light propagates through space and how its properties change due to the expansion of the universe. The redshift of distant galaxies, caused by the stretching of light wavelengths as space expands, provides direct evidence for cosmic expansion and allows us to measure the universe's age and composition. Future telescopes will push even deeper into the past, potentially observing the first stars and galaxies to form after the Big Bang. These observations will test our understanding of cosmic evolution and the fundamental physics that govern how structure forms in an expanding universe. The speed of light limit ensures that these observations provide genuine glimpses into cosmic history, rather than just snapshots of the current state of distant objects. Without this finite propagation speed, astronomy would be limited to studying the present universe, missing the rich evolutionary story that unfolds over cosmic time. Gravitational wave astronomy provides another window into this cosmic history. The advanced LIGO and Virgo detectors have observed dozens of black hole and neutron star mergers, each one a direct observation of space-time itself vibrating at light speed as massive objects spiral together and collide.